In a previous video, I talked about entropy using the definition S equals k natural log of omega. The idea was entropy was defined as the natural log of the number of microstates of our system corresponding to a given macrostate times Boltzmann's constant k. We did some calculations with that, but what I didn't do in that video was talk about what entropy means. And that's a really important thing. I've got some reference stuff here that I'm going to work with later, but I want to focus on just the meaning of entropy first and talk about it. And when you hear people talk about entropy, it's almost always described as a measure of the disorder of a system. And there's some real truth to that. Talking about entropy as a measure of disorder says a lot about what it means. Fundamentally, we know what it's really measuring is multiplicity. Entropy increases when the number of ways of creating the same macrostate is greater. And entropy is lower for a macrostate if there are fewer microstates that give rise to that same macrostate. So by saying disorder, our formal definition of disorder is just sort of from our big macroscopic point of view, looking at some system where we can't tell the difference between microstates. How many ways are there of doing that, of having the system in that macrostate? That's what we mean by disorder for entropy. It's just how uncertain are we? How much lack of knowledge we have of that microstate? There's some very low entropy state. There might just be one way or a handful of ways of creating that total energy in the system or that temperature in the system. For a highly disordered, high entropy state, there might be 10 to the 23rd ways of creating that much disorder. So that's where entropy as disorder comes from. And one of the things, so we've got that idea. One of the things I want to focus on now we know the conceptual idea. I want to talk about how you use entropy in calculations or how you think about it in calculations. Again, we'll do more calculations with entropy later, but in terms of thinking about entropy, one thing to point out is that the entropy of a system is always going to be a state function. It's a function of what the state of the system is right now. It's not a function of how you got there. So some things, work done in some process are not state functions. It matters how you get from state A to state B, what the work was done in between. But entropy is all a question of just what's your state, here's your entropy. And that leads to some really interesting things we'll see later about the fact that you can calculate the entropy difference between two states and along some process you understand well, and then deduce what it must be for a process you don't understand as well. Even if the process was totally different that got you there, the change in entropy has to be the same. So it's a state function, a lot like the energy of a system is a function of the state of it, or the volume of a system is a state function. The mass of a system is a state function. One thing that entropy is not, though, is conserved. And this is one of the fascinating things about entropy that makes it feel strange compared to the other quantities that we've spent a lot of our lives as physicists studying. Entropy is not conserved. Many processes, I might go so far as to say the vast majority of processes in the universe, for macroscopic objects, almost everything, will create new entropy as things go on. And there are lots of examples of that. We'll talk about a bit of it. I want to talk about that today to get a sense of how this works. So the example I want to look at to illustrate some of these points, the state function point and the creating new entropy point, the example I want to get at is I'm going to look at the expansion of a gas. I'm imagining an ideal gas, a monatomic ideal gas, pretend it's helium just for kicks. And I'm going to have my helium in this container that has area A and length 2L, but there's going to be a piston that's holding all the gas in the left half of the container. So length L, the piston is there. And what we want to do is look at ways of changing the state of the system to a state where the gas fills the entire cylinder of length 2L instead of just half of it of length L. And we're going to look at that. We're going to look at that expansion, the expansion of the gas from a volume to twice the volume. We're going to look at that in a few different ways. So to begin with, I want to go and talk about a couple of just facts we're going to use about ideal gases. And the first one is the Sackur-Tetrode equation for the entropy of a monatomic ideal gas. This equation, you can work it out just by calculating out things from the ideal gas law and from the multiplicity of an ideal gas calculated in various ways. If you calculate that out, use Stirling's approximation, you can get this. I'm going to just start from this Sackur-Tetrode equation for the multiplicity for the entropy of a monatomic ideal gas and just work with it. So this is going to be our state function for entropy. I will point out, I'll come back to this in a bit, that because this is a natural log inside of here, natural logs let you split things up in interesting ways. And in particular, we're going to find it's possible to write this natural log as a natural log of blah equals natural log of the volume V plus natural log of a bunch of other crud. And splitting that up, we'll have just one term in this whole equation that depends on the volume. Since we're changing volume, that's going to be the thing we care most about. One term that depends on volume, and a bunch of other terms that depend on n and k and u and all sorts of things, but not on the volume. Saccharotetrode, by the way, I should be clear, depends on the number of particles n, the volume v, the mass m of the particles in the gas, Planck's constant h, and u, the total energy of the system. It's a little weird to specify total energy instead of temperature or something. That's because we're looking, again, sort of a microcanonical ensemble picture. We're looking at this idea, counting individual microstates for a specified macrostate u. That's where we are on this, so that's what saccharotetrode is based on. The other couple of facts I'm going to remind you of that will come up later are, first of all, for an ideal gas, a monatomic ideal gas, the equipartition theorem tells us that the energy of the gas is 3/2 nkt. And we're going to talk about adiabatic stuff eventually. For a quasi-static adiabatic expansion or compression of a gas, there's this relationship that the volume times temperature to the 3/2, again, this is for a monatomic ideal gas, V times T to the 3/2 is a constant. Whatever the heck that constant is, it's a constant over the course of your interaction. Okay, that's my sort of background stuff. We'll come back to it eventually. I want to explain why it's here. So I want to look at the expansion of this gas in 3 different ways. And those 3 different expansions are going to be, there's going to be a quasi-static isothermal expansion. Isothermal, remember, means constant temperature, which for us will also mean constant energy. Quasi-static means that the system remains in equilibrium as you carry out the process. So you're going slowly enough that the pressure and temperature and things have time to equilibrate throughout the system. So we're going to expand our gas in 3 ways. So expand the gas in 3 ways. And our first one, as I said, will be a quasi-static isothermal expansion. So, quasi-static isothermal. So that tells me that T is constant, and if temperature is constant for our ideal gas, then U is constant. So we know that our U is a constant here in our process. And of course, for any of this, we're not letting molecules of gas escape or atoms of gas escape. So N is a constant. We're not changing the gas. So mass is a constant. So the only things that are changing here, the only thing that's changing is V in this thing. So we want to say, what is our delta S going to be? Our delta S is S final minus S initial. That's what delta S means. And we're going to use the fact that these things, only V is changing in the Saccharotetrode equation. So these things are going to be a constant. They'll cancel out, right? S final minus S initial is going to be equal to, what do we have? We have NK natural log of V final plus constants minus NK natural log of V initial plus constants, the same constants. And so the constants will cancel out when we subtract. And we're going to just get NK natural log of V final minus natural log of V initial, which is the same as NK log identity here, natural log of V final over V initial. I want to say that the mathematical comment, just to put it out there, I feel way happier once I get to this step than I did in the middle, because this line here, this line where I've split this up in natural log of V plus natural log of the rest of the stuff, that this splitting up actually is mathematically a terribly bad idea. Why? Because the argument of a natural log function should always be dimensionless. And I have something here with units of meters cubed or something. It's not dimensionless at all. It's got units of volume. So natural log of meters cubed is a horrible concept. You don't want it at all. If I were really going to do this formally and do math with it, I couldn't do it this way. You'll see up here I'm okay because I've got a natural log of a bunch of crud, but V has units of meters cubed, say, in SI units. And this whole thing, if you plug in Planck's constant as units of joule seconds, kilograms, joules, if you plug it all in together and you reduce it, you'll get 1 over meters squared to the 3/2, 1 over meters cubed. The thing in the parentheses here is dimensionless. So really, if I wanted to be really careful about this, I would write this as a natural log of V over some V naught, some reference volume I come up with just arbitrarily, some number I make up to make it dimensionless. Mathematically, we can get away with not doing that, but it always makes me feel better at the end to express to use log identities to express my log in terms of this ratio. And hey, for us, V final is exactly 2 times V initial, right? So this is NK times the natural log of 2 is going to be our change in entropy of the system. NK times the natural log of 2. That's our delta S for a quasi-static isothermal situation. Our entropy of the system has gone up. By the way, if you go through this process and you've kept it isothermal, you'll find that you had to have done that when this plunger, when this piston moves out of the way, out here, the gas molecules that are hitting it as it moves will lose energy as they bounce off. It's the opposite of compressing the gas. You're expanding, the gas molecules are bouncing off that and coming away because it's moving, because the plunger's moving. When they bounce off, they'll leave with lower speed. We lose energy in this process. And so to keep this isothermal, we must have been at the same time putting it over a Bunsen burner or something. We must have been pumping heat into the system to make up for the negative work on the system being done by expanding this piston. We did negative work by this gradual expansion. We put in heat from outside. It kept it isothermal. We increased the entropy. Interestingly enough, because we had to put in heat from outside, that means that the outside world must have lost energy via heat. And losing energy in the outside world means the outside world's entropy will have gone down. So there's some balance that happens there along the way, with the outside world's entropy going down and the entropy of the gas going up. You have the potential for some balance between the two. I'll comment on that. Delta S of the environment must have been less than 0 to add heat into our system. So we had that going on. Okay, so that's our first way of expanding this gas. Clearly I've not planned well in terms of where to put my words and things here, but we'll see where it goes. My second way of expanding the gas is the other type of expansion that we've looked at in detail is quasi-static, because quasi-static is easiest to deal with, adiabatic expansion. Quasi-static adiabatic expansion is adiabatic, remember, it's still quasi-static, so it's still in equilibrium the whole time, but we're going to expand fast enough that there's not time or opportunity for heat to come in from the outside and change our system. We've got, the idea here is that heat equals 0 for an adiabatic process. That's what adiabatic is all about. Heat equals 0. And so if the heat is 0, Q equals 0, that leads to our results like this one. V times T to the 3/2 is constant. Got that. But hey, just throwing this out there, if V times T to the 3/2 equals constant, and U is just some constants times T, in the equipartition theorem, that tells us that in this situation, V times U to the 3/2 is a constant, right? V times U to the 3/2 is a constant, and hey, inside the natural log, we've got V times U to the 3/2, and everything else is constant. So from soccer tetrode, S is constant, and delta S equals 0. There's no change in the entropy of our gas when we expand it. This is actually a defining property of quasi-static adiabatic things. It's isentropic. The entropy doesn't change. So delta S equals 0, and because Q is equal to 0, we insulated ourselves from the environment, so there was no interaction with the environment at all, apart from this plunger moving. We also have delta S environment equals 0, because the environment didn't have any entropy changes. I guess the one thing I can say is that because this is constant V went up, we should say that T is lower, and so the energy is lower. Just to emphasize that, we had a different endpoint. So it's actually not a problem because these have different endpoints. The state is different. It's not a problem. We have different changes in entropy. We started from the same entropy, whatever it was to begin with. This one increased its entropy. This one didn't. But where the isothermal case, we expanded this and the average energy of the particle stayed the same. In the adiabatic case, we expanded it and the average energy went down, right? The energy and temperature went down, again, because we were losing energy in those collisions with that moving piston. Every time it hit that moving piston and bounced off, it lost energy. The atoms lost energy. We lost energy and we didn't put any new energy in from the environment. So this is why here we ended up with a different we ended up with the same final entropy instead of an increased final entropy. We had more position states that we added, but we got rid of momentum states because the molecules are moving slower. The atoms are moving slower now. Okay, that's two ways of expanding the gas. Those are the two that are most straightforward, but let me tell you a third way of expanding this gas. And I'm going to go ahead and just put it over here and get rid of our original definition up here, just to write it down. Our third way of expanding the ideal gas is going to be just what's called free expansion. Instead of pulling the barrier smoothly away quasi-statically, we're going to do the opposite of quasi-static. We're going to just instantly remove the barrier. So if you want to, I could even redraw this a little bit really quick, right? I could say I had the system that had my long tube, and I had my barrier in the middle that was here, and I had my gas on one side only. That was supposed to be the very middle. Don't worry if it's not exactly. Okay, there we go. I got that. And what I'm going to do for free expansion, you can almost imagine that's just like a bubble, the surface of a bubble there. I'm just going to pop the bubble. Just going to go, nope. We pop the bubble, and the gas is then suddenly free to move into the other side. If you just pop that bubble, just get rid of the barrier instantly, the gas, well, they were all bounced around here. Now they're just going to wander into the other side. What's the final state here? We haven't studied free expansion before. We haven't looked at it. So I should emphasize very explicitly that this is not quasi-static. Why? Because when you pop that barrier, over on this side, it's still for full pressure, while these molecules are just woo, going off into the distance. It's not in equilibrium throughout the region. Zero pressure, high pressure, right? So it doesn't stay in equilibrium the whole time. We have to reestablish equilibrium eventually. In this case, well, what do I know? What changed and what didn't? In this case, I know that there's nothing that acted on these molecules to speed them up or slow them down. The average speed has to be the same. Each individual molecule's speed has to be the same at this point. So U didn't change because no molecule speed changed. We know that U didn't change. N didn't change, of course. And we know that the volume went to 2 times the volume. V final and I guess V final equals 2V initial. We just made that instantaneous change. Well, that's enough to do our entropy function, right? That's enough to say U was constant, N was constant, V changed. In fact, it's the exact same entropy as we had for quasi-static isothermal. That tells me that delta S is exactly what we had over here. It's Nk times the natural log of 2. But it was a totally different process, and yet here, what happened to the environment? Delta S environment equals 0 because it wasn't affected at all. We just popped a bubble. We just removed a barrier. We just opened the barrier. Delta S environment is 0. And so comparing these two, here, the final state for 3 and 1 is exactly the same. Entropy is a state variable. The final state is exactly the same between the two. But in this case, the outside environment stayed the same entropy, whereas in this case, the outside environment lost entropy to balance out the gain here, at least partly. You can see that what's happened here is that this process of popping the bubble or removing that barrier instantly, this process of free expansion created entropy out of nowhere. Here you could have at least hoped that the two would balance out, and if it was slow enough, they would. You could have at least hoped that these two things, the increase of entropy of the gas and the decrease of entropy of the environment, you could hope maybe delta S total equals 0. Again, if it's very, very slow, it would work out. Here, delta S total was 0. But here, it's obviously true that delta S total is NKLN2. We increase the entropy of the universe by popping a bubble. We increase the entropy of the universe just by pulling a barrier out of the way. No entropy anywhere decreased to make up for this. Entropy just showed up. That's the thing that makes entropy interesting. That's what makes it a really different concept than other quantities that we work with in physics. And it's kind of cool to work out the implications of that, when it happens, when it doesn't. There's a lot of depth and a lot of intuition and a lot of understanding that comes from doing that. So I'll stop with that. That's my conversation about the meaning of entropy and how it behaves. We'll do a lot more with it eventually in our class, but I hope this at least gives you a flavor of how entropy is and isn't like some of the other quantities that you may have studied in physics.